You know, when scientists are trying to understand a disease, they're often staring at a mountain of genetic data. We're talking thousands upon thousands of clues. But here's the catch. Most of that is just, well, it's just noise. So the real challenge, the big mystery, is figuring out which of those clues actually matter. And that's exactly the genetic whodunit we're diving into today. So let's put you in the shoes of a detective for a second. You've got a crime scene, and in front of you is a lineup with thousands of potential suspects. How in the world do you zero in on the one who's really responsible? Believe it or not, this is pretty much the exact problem geneticists face every single day.
And this isn't just a metaphor. For the famous leukemia dataset we're going to look at, scientists started with exactly this many potential suspects. That's 3,051 different genes. The mission? Figure out which of them are the key players that can tell us the difference between two types of leukemia.
But here's where the plot thickens. When you have that many suspects, you run into a huge trap. It's called the multiple testing problem. Basically, if you test thousands of things at once, some of them are going to look important just by pure random luck. It's a statistical coincidence. And for our detective, this is the biggest hurdle. How do you separate the real, meaningful leads from all the false alarms? So, how do we get around this? How do we find the real signal in all that noise? Well, thankfully, scientists developed a pretty slick tool, a kind of statistical detective, you could say, built for this exact kind of investigation. And its name is SAM. It stands for Significance Analysis of Microarrays. I know it's a bit of a mouthful, but what it does is actually pretty brilliant. Its whole job is to slice right through that random noise, look at that massive lineup of over 3,000 genes, and pinpoint the ones whose behavior is genuinely different between, say, two groups of patients. So, how does this detective do its job? What's its secret technique? Well, Sam uses this incredibly powerful, yet elegantly simple idea. Instead of just looking at the evidence once and calling it a day, it shuffles everything around to figure out what a coincidence really looks like in the first place. Okay, so here's how Sam pulls this off. First, it looks at the gene patterns in the actual, real patient groups. Simple enough. But then, here's the clever part. It takes the patient labels, like cancer type A and cancer type B, and it just shuffles them up randomly. It reruns the analysis on this jumbled up data to get a picture of what a random, meaningless pattern looks like. And it doesn't just do this once, it does it hundreds of times to build a really solid baseline for what pure chance looks like. Finally, it takes the real results and compares them to that random baseline. Only the genes that stick out way, way above all that noise get flagged as the real deal. And all of this shuffling allows us to calculate something absolutely crucial: the false discovery rate, or FDR. The easiest way to think about this is as the false alarm rate. By knowing what randomness looks like, Sam can actually estimate what percentage of the genes it flags might still be a fluke. And the whole goal, of course, is to keep that number as low as possible, so we can be really confident in our final list of suspects. All right, enough theory. Let's get our hands dirty and apply this to our real-world case file. We're going back to a groundbreaking 1999 study by Galoob and his colleagues, which was all about figuring out the genetic differences between two types of acute leukemia. Now, the raw data itself looks something like this. It might seem complicated, but it's pretty straightforward. Each row represents one of our 3,000-plus genes. Each column is a different patient, and the numbers in the cells tell you how active that specific gene is in that specific patient. Sam's job is to scan all these rows and find the ones where the numbers are consistently and significantly different between our two leukemia groups. And speaking of our groups, here they are. In this particular investigation, we have 38 patients in total. You can see that 27 of them had a type of leukemia called ALL, and the other 11 had a type called AML. Sam's entire mission is to find the unique genetic fingerprints that separate these two groups. Okay, the stage is set. We've got our data, we've got our patient groups, and we've got our detective, Sam. It is time to sift through the evidence and identify the real genetic culprits that distinguish ALL from AML. But we can't just tell Sam, hey, go find the different genes. We have to be more specific. We need to define how different a gene has to be considered important. And we do this by setting a threshold, a parameter called delta. Think of it as telling our detective just how strong the evidence needs to be before they can officially name a suspect. Now, setting this delta is a real balancing act. If you set it low, that's like being a very lenient detective. You're going to flag a lot of genes as suspicious, but you'll also have a much higher risk of false alarms. On the flip side, if you set delta high, you're being super strict. You'll flag way fewer genes, but you can be a whole lot more confident that the ones you do find are the real deal. So for this leukemia analysis, the researchers decided to play it safe. They took a conservative, strict approach. They tweaked that delta parameter to a value of 1.11, and they chose that specific number to hit one key target. They wanted to make sure their false alarm rate, that false discovery rate we talked about, was less than 5%. Basically, they chose high confidence over a long list of suspects. And the result of all this careful, rigorous work? Well, it's pretty dramatic. We went from that initial, chaotic crowd of over 3,000 potential suspects all the way down to a small, manageable lineup of the most wanted. By using SAM with that strict threshold, the scientists were able to isolate just a handful of genes that were truly, meaningfully different between the two types of leukemia. This gave them a crystal clear set of leads to investigate next. So we've done it. We've gone from a mountain of messy data to a short list of high-confidence genetic leads. And this, of course, leaves us with the most important question of all. Now that we have our prime suspects, what's next? How do we take this knowledge and turn it into better ways to diagnose, to treat, and maybe, one day, even cure diseases like this? Well, that is where the next and most exciting chapter of the investigation truly begins.